I'm so excited to present Beyond the C retargetable decompilation using neural machine translation. And so let's start with decompilation. I think Fish just called this the crown of binary analysis. And so this is very important to analyze malware, patch vulnerable software, or audit closed source libraries. And the way that traditionally this is being done is the native code is lifted to some IR, and then based on some analysis and inference on that IR, we synthesize high-level code from the CFG. And so kind of like the magical ingredient in many of the current solutions is that they lean on C, and it's like there's an assumption that we want to generate C as the high-level language, and the code that we're dealing, the machine code, supposedly came from a C program. And one of the issues with that, that they're prone to emitting go-to statements, was also mentioned. And so these are the current state-of-the-art decompilers out there, Hexrace and Binary Ninja, which are commercial, and Ghidra and RedDec are among the open source solutions. And so all these current solutions are really complex, costly software to develop that took a lot of time to make. And they're also not based on the premise of really generating human-friendly code. The issue is that we might want to reverse a Go or Rust malware. So we have this motivation for retargetability in terms of the high-level programming language. And for example, Rust was released a decade ago, and it's already being used in malware in the wild. So it's a very fast-paced environment. So here is an example of trying to decompile a very simple Go function with Ghidra. And again, this the executable was generated without stripping the binary or optimizing or applying any obfuscation. But even in the simple case, we see that the traditional solutions are just bad at decompiling non-C programs. And so neural decompilation, the question was asked, like, what if we applied NMT methods to decompilation? And so, for example, in 2018, Katz and others applied RNNs to this problem. Their solution included modifying a C-line compiler, and it was limited in terms of the length of the snippets that they would consider. And that's one of the issues with these methods. And then 2019, Fu and others introduced the CODA. They added an additional error correcting stage, and they used instruction type awareness, and their solution worked with the AST representation of the code, and still this was a RNN-based method. And so prior work leans heavily on C, and the data sets are limited and lacking. For example, CODA is tested on Hackers Delight loop-free programs, which are programs that do not include loops. And they also use some narrow synthetic data that generated a simplistic math expressions without and called argumentless functions only, which are far from real-world examples of programs. And so these solutions are really not retargetable. And the challenges to being retargetable is, one of them is compiler integration. So if your solution is using a C-line pass, or you're tweaking some compiler for that, and then you want to use it for a new programming language, you have to redo that part and do the integration for a new programming language or a new compiler. If you're working with abstract syntax trees, or you have to use some parsing and lexing, again, you're bringing some domain knowledge based on that programming language or that assembly that you're using. So these are the main challenges to having retargetable solutions. And so what we asked was, what if we treated code, both the assembly side and the source side, as plain text, so that there will be no more compiler integration, no longer requirement for parsing or AST or anything, just plain text. And so basically minimizing language and target specific knowledge and trying to get the most out of the least domain knowledge that we can. And the motivation would be that NMT and NLP have progressed a lot recently. And so let's just use what NMT has to offer. And so we assessed viability of discarding any language-specific knowledge by treating code as plain text. And we demonstrated retargetability by applying our system to 4 programming languages. One of them is C, but 3 others have never been subject to research in decompilation, as far as we know. And we provide evaluation of the models, and we will make our training corpora models and code available so that hopefully it can be used in the future by others. And we also have a small VS Code extension that lets you to view a decompilation model in action with like highlighting the tokens based on the scores that come out of the model. And so the general architecture of this solution is that we start with some code repositories, and then we have some source files, and then we can, by compiling them, we can get some assembly files. And the whole process is done per language. So we train a separate model for each language. And so after having some source files and assembly files, we have a pair generator that just matches up functions. So for each function, we get a pair, which includes the source representation of that function and the assembly representation of that function. And then we train two separate tokenizers on the one tokenizer on the source example, on the source representations, and one for the assembly side. And then we use this tokenizer to train a transformer model on this. And in the end, we get a trained transformer model. And these tokenizers, we can use it to predict or to decompile new functions. And again, so in the whole process, we don't bring in any domain-specific, we minimize the usage of any language-specific knowledge in each step. And so the 4 languages we picked were C, Go, OCaml, and Fortran, and we kind of picked them. We tried to pick a variety of languages, including like having a functional language in the mix to kind of assess how the results would be different. And so for data acquisition, the CATS paper, they were using programs that compile with minimal modification from some Fedora projects. So obviously in all prior work as well, there's an incentive to obviously go with programs that are easy to compile or work with. And Coda used the synthetic sets composed of math expressions and argumentless functions. And they also used had a real set, which the real set was Hacker's Delight, which is a set of loop-free programs. Another example of the length limitation we mentioned, in the CATS paper, they have 4 different buckets based on the maximum sequence length, and the smallest bucket includes 5 C tokens, 5 high-level tokens. And as an example, like a simple snippet like X equals Y plus Z semicolon is 6 tokens, which means that it wouldn't fit in the smallest bucket. So there's really, when you have really small snippets, there is only simple things that you can do with those number of tokens. And so for our data acquisition, we didn't use any synthetic data. We only used the data that was real programs in the wild. And we started with gathering data for C, and we went for competitive programming and interview questions, again, based on that incentive that these are usually single source and easy to compile programs. And we did the same with Golang, added in some utility programs and general algorithms. And then starting with Fortran, we realized nobody is solving lead code programs or interview questions with Fortran. So we went with computational code like flow solvers and ODE solvers. And we think this is a good choice, not just because there doesn't exist any interview questions, but also because this reflects how Fortran is also used in the wild. And for OCaml, we used packages from the OPAM repository, and we picked a bunch of core packages and the binary analysis to BAP. And we also we wanted to know like how does the whole process scale for more data. So we later also gathered 2 larger corpora for C and OCaml, which the C version included millions of functions. And so for tokenization, for both tokenization and training the transformer, we used the solutions that were already out there. So for training the transformer, we used the solution by FairSec, which is an open source Facebook AI library. And for tokenization, we used the BP tokenizer by Hugging Face, which is a subword-based method. And for evaluation, taking the same terminology as in CATS, we measure average edit distance. So for any sample, we take the edit distance between ground truth and prediction, and then normalize it by length and average over the sample. And this is summary of our evaluation results for the different languages. And as it can be seen, it's different for different languages. And the worst score is for OCaml. And so here we do a comparison with the CATS example. And in their evaluation, obviously they only have C evaluation. And also it should be noted that we're doing function-wise snippets, and so our maximum token lengths are much larger than the sequence lengths that CATS handles. But also part of this is that because this issue with large sequences is even worse with RNNs, but we are using a newer transformer model. And so here we see an example of the model in action. And one of the observations from this is that, well, the whole edit distance evaluation is not perfect, because sometimes you can have semantically close predictions, but in terms of edit distance, it would be penalized. Like in the C example, that we can have we can have different forms for a loop. For example, we can have we have it in a while form or a for loop. In terms of edit distance, we don't see that these are close predictions because we get penalized for that. But also we realize that some high level structure is kept correctly. And so generally, compared with the traditional solutions, in traditional solutions, we sometimes see that the decompilation has issues that the output is not human readable. Well, here, or we might have like go-to statement, which is something that a C programmer wouldn't use go-tos, but we will see them in the prediction. Here, the type of errors that we see, we don't see those kind of errors, because based on the training, if the training does not include many go-to statements, the predictions, you wouldn't see go-to statements. But the type of errors we see here is that we can see in the Fortran example, there is a simple increment by 1 in one of the lines, but the model gets this wrong, even though this looks like a simple thing to decompile. And so one of the results, the takeaways from this is that looking at the C solutions that are out there, they're production ready and they're doing a good job. So it really does seem that end-to-end decompilation methods would not be able to go head-to-head and like be production ready or be competitive with them. But if we go beyond the C, the traditional methods are having a struggle to decompile non-C programs. And so we think there might be room for neural decompilation methods not to compete with the traditional methods, but be maybe used as a complementation, be used beside them, especially for non-C languages where traditional decompilers falter. And so the limitation is that, like, to be frank, it's clear that ND still has a long way to go, and the results are not even close to the production grade C decompilers that we have, for example. But it should also be noted that we shouldn't discredit the ML-based method completely, because the large language models that are being trained, there are models being trained in the range of hundreds of billions of parameters, or with very large data sets. But in neural decompilation, we're not even seeing numbers close to that. So for example, in our work, the largest model was only 200 million parameters. And even though there are terabytes of code on GitHub that can possibly be used for training, the data sets that are being used in neural decompilation work is not close to that. Another limitation is interpretability. So this is a general issue with deep learning methods, that you kind of have a bunch of weights to deal with, and it's not easy to see how the results are actually generated. Where in the traditional methods, you can go back to the different passes or the lifting stages that you had and be able to pinpoint where something is going wrong or not. And in the same vein, it's hard to have provable semantic correctness with ML-based methods. Another issue is long sequence length. So NMT methods have a general limitation that if you have larger sequence length, you will run into trouble. But this is a general ML issue. And as we saw here, it will get better with advances in ML. The prior work to us was using RNN-based method. New ML advances led to transformer models, which let you do larger sequence lengths and don't suffer the consequences that much. And another issue was that there was little open source work and data or any demonstration or evaluation for any retargetable approach that doesn't concentrate on C. And so to help with that, we hope that we're helping with that by sharing our data and code. And for future work, BTC's main advantage is its simplicity. And so this approach can be used in conjunction with other methods. Evolving exact decompilation was mentioned in previous talks. And so they have a sketch-gen part. And so this BTC can be used as part of their solution. And there are also other canonicalization techniques, for example, that try to take all the different forms of a for loop, for example, normalize them to one form so that the ML model can better learn and not be better learn the specific kind of for loop. And another issue is another way future work can be interactive UX. So Fishfang mentioned collaborative reverse engineering. So here we can also think that the auditor, the human element, collaborates with the machine learning model by, after it gets a prediction, tries to fix or change some of the tokens and then send it back to the model to get a new prediction. So this is also something that can be looked in the future to have an interactive solution wherein the human element is part of the loop. And in conclusion, we want to say that ND looks promising, and with right design choices, it might be able to deliver on the promise of retargetability, and little domain knowledge can go a long way. And there is room to explore this problem if we go beyond just doing C programs, trying to decompile C program. Thank you.